Hi everyone and welcome. In this video we will explore how the rationals and irrational numbers sit within the set of real numbers. And so the first theorem is about the density of the set of rational numbers within the set of real numbers. And it states that between any two real numbers a and b, no matter how close a and b are to each other as long as they're not the same, then there is a rational number in between them. To prove this result, our goal is to find a rational number in between a and b. In other words, we need to find an integer m and a natural number n so that their ratio is greater than a and less than b. We begin by considering the distance between a and b. In other words, the length of the interval from a to b. And this length might be very tiny, but regardless, by the Archimedean property, there must exist a natural number n large enough so that the quantity 1 over n is strictly smaller than b minus a. And this helps us fix n, which is going to be our step size. If you consider the following diagram where we have the points a and b labeled in blue, what we would like to do is pick a rational number in this interval. And so by choosing the quantity 1 over n small enough, specifically smaller than the length b minus a, then it ensures that we can never overstep the interval ab. And so you can see our step sizes are strictly smaller and eventually we will end up landing within the interval. So now with n fixed, we're done half the battle. Next, we need to find an integer m so that the following holds. But instead of working with this, let's multiply both sides by n, which we can do since n is a natural number and hence positive, to work with the following inequality. And this inequality is slightly easier to work with because now we're looking for an integer m, which is strictly larger than some real number and strictly smaller than another real number. The trick is to let m be the smallest integer larger than the real number na. And although this seems plausible and intuitive, how do we know that such an m even exists? Well, in order to show that such an m exists, we will have to use something that we haven't really covered. It's something called the well-ordering principle. But for those that are interested, let me briefly go over why such an m exists. Let's begin by considering the set S, which is the set of all integers strictly larger than na. And what we are after is actually the smallest integer larger than na. In other words, the smallest member of S. Well, in the previous video in which we covered the Archimedean property, we saw how the set of natural numbers are unbounded from above within the set of real numbers. In a similar fashion, we can actually show that the set of integers are also not bounded above in the set of real numbers. And so there must exist an integer that is strictly larger than the real number na. And so therefore, the set S here is actually non-empty because there is actually an integer which is strictly larger than the real number na. Moreover, the set S also happens to be bounded below. An example for a lower bound is, for example, the number na itself. And so now there's something called the well-ordering principle, which says that if you have a non-empty subset of integers which are bounded below, then it has a least element or it has a minimum. And so therefore, this allows us to say that the set S here does indeed have a smallest element. And so this is why there is a smallest integer larger than na, and we can call that m. The second thing to note is that what I have written here as an inequality does not fully capture what I have written in words above. This inequality is simply asserting that m is strictly larger than na. But we actually want m to be the first integer larger than na. And so I claim that m also satisfies the following condition. That is, m minus 1 must be less than or equal to na. To see why this is true, let's suppose for contradiction that actually m minus 1 happens to be larger than na. Well then, m minus 1 would be an integer which is strictly smaller than m, but also greater than na. And so this would contradict the fact that m was supposed to be the smallest integer satisfying this condition, right? And so therefore, actually, m minus 1 should be less than or equal to na. And overall, what we get in the end is that m is larger than na, but m minus 1 is less than or equal to na. And this statement here exactly captures what we wrote above here in words, that m is actually the smallest integer or the first integer larger than na. Now we can use this established relationship to finish off the problem. From m being strictly larger than na, we can divide both sides by n to get this. In other words, our constructed rational number is strictly larger than a, and now we just need to show that our constructed rational number is also less than b. Recall that we picked our n so that 1 over n is strictly less than the distance between b and a. Well, we can multiply both sides of this inequality by n to get the following equivalent inequality. And now let's use the other relationship that we established, which is that m minus 1 is less than or equal to na. Well, let's add 1 to both sides of this inequality And that gives us that m is actually less than or equal to na plus 1. And now we can replace this 1 by what we have here and simplify. So we have that m is less than or equal to na plus 1, and then this must be less than na plus this quantity. And again, this is because 1 is strictly less than this quantity, and so what we can do is replace this 1 to get something larger. And now notice the na and the minus na cancel out, and we simply get nb. Overall, if you look at the extreme left and extreme right, what we get is that m is strictly less than nb. And finally, let's just divide both sides by n, and we get that our constructed rational number is actually less than b. Overall, we see that our constructed rational number, m over n, is larger than a and smaller than b. And this is exactly what we wanted. We wanted to find a rational number in between a and b. And this completes the proof that between any two real numbers, you can always find a rational number. Next, let's talk about the density of the irrational numbers within the set of real numbers. It turns out that between any two real numbers a and b, with a less than b, there exists an irrational number t strictly between a and b. And the proof of this result follows very nicely from the density of the rational numbers. So let's begin by letting a and b be two real numbers with a less than b. And then let's subtract the square root of 2 from both sides of this inequality. And so geometrically, what we have done is just shifted the interval by square root of 2 units to the left. Now notice that a minus the square root of 2 and b minus the square root of 2, they're two real numbers. And so now by the density of the rational numbers, there must exist some rational number in between these two real numbers in this shifted interval. Next, we will add square root of 2 on each term of this inequality. And what we see is that this number r plus the square root of 2 is strictly between a and b. And now the claim is that this number r plus the square root of 2 is actually an irrational number. To see why, let's suppose for contradiction that r plus the square root of 2 is actually a rational number. In other words, r plus the square root of 2 happens to be a ratio of two integers, right? It's equal to p divided by q, where p is an integer and let's say q is a natural number. Well, now let's subtract r on both sides to get the following equation. And now we have a rational number, subtract another rational number. But the set of rational numbers is actually a field. It's an ordered field, right? And so it's closed under the operation of addition. And so what this means is that this result is actually a rational number. In other words, the square root of 2 must be rational. But this is clearly a contradiction because the square root of 2 is actually an irrational number, as we have previously already seen. And so therefore, this number r plus the square root of 2 is actually an irrational number. And so there we go. We have found an irrational number strictly between the real numbers a and b, and that completes the proof. And so in summary, what we see is that between any two real numbers a and b, there is always a rational and an irrational in between those two real numbers. This is actually what we mean by density. The set of integers and the set of natural numbers, they're not dense, because between any two real numbers, there may or may not be an integer or a natural number. But it is always the case that between any two real numbers, no matter how close they are to each other, you can always find rational and irrational numbers in between them. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.